While MiG-15s and Sabres were battling in the skies over Korea, a radical new aircraft was taking shape on the drawing boards at Lockheed. When it appeared in 1954, the new F-104 Starfighter promised to double the speeds at which aircraft could fight. Its extraordinary looks and speed earned it the nickname of the Zipper, or the missile with a man in it. However, its early service career was marred by numerous fatal accidents, and it was soon being referred to as the Widowmaker. While there certainly were technical issues to be resolved, much of the unfortunate reputation was down to the inexperience of pilots who were new to the perils and pitfalls of Mach 2 warfare. The F-104's career with the US Air Force, including combat operations in Vietnam, was undistinguished, but the type matured to become the backbone of NATO air power in Europe, where its blistering low-level speed made it ideal for interception, fighter bomber and reconnaissance duties. With its accident-strewn days long behind it, the F-104 finally lived up to the one nickname that endured throughout its career, the Star. Built for speed, the Starfighter was like no other aircraft. The long, slim fuselage had a high fineness ratio for maximum speed and was highly streamlined. The tiny wings measured just 2.3 meters from tip to root and appeared barely adequate to keep the aircraft in the air. Compared to some of its contemporaries, the F-104 was a small aircraft. Lockheed had examined several larger twin-engine schemes, but settled on making the Starfighter as small as possible. In weight terms, that meant the Starfighter tipped the scales at around the same empty weight as later Sabre variants, although its maximum takeoff weight was greater. In speed terms, the F-104 set the benchmark for virtually all warplanes to follow, and Mach 2 remains the basic top speed for most fighters today. The F-104 was limited to Mach 2 compressor intake temperature limits. As well as double sonic speed, the Starfighter could climb at rates previously only dreamt of. This was particularly appropriate for the interception role, and it could also attain altitudes considerably higher than those achieved by other fighters. This performance came at a cost, however, and the Starfighter was never known for its range. With wing tanks and careful flying, range could be eked out to over 1,000 miles in the F-104G, but any use of afterburner would quickly eat into that figure. Eager to demonstrate the performance of its new fighter, the US Air Force established absolute speed and altitude records in May 1958 using a YF-104A. This was the first time a single type had held both records. A series of extraordinary time-to-climb records were established in December that year. A year later, Captain Joe Jordan used an F-104C to set an altitude record of over 103,000 feet, during the course of which the aircraft reached Mach 2.36. Much later, in 1977, a modified Starfighter known as the Red Baron established a low-level speed record of nearly 1,000 miles per hour. The highest performing Starfighter, however, was the remarkable NF-104A, 3 of which were produced to provide high-altitude control training and zero-G experience for potential astronauts and test pilots. The 3 surplus F-104As were returned to Lockheed in 1962 for extensive modifications. The intake shock cones were modified to raise limited airspeed from Mach 2 to Mach 2.2, and the wingtips were extended by around 0.6 meters to increase wing area. They had an F-104G style extended rudder, which was powered. At the base of the fin was a fairing housing a Rocketdyne LR-121 variable thrust rocket fueled by a mix of JP4 kerosene and high-test peroxide. This added around 6,000 pounds of extra thrust at full throttle and took over from the standard J79 engine when it became oxygen-starved at high altitude. At the extreme altitudes that the NF-104A was expected to reach, the air was too thin for conventional controls to work, so the NF-104s had a series of reaction control nozzles mounted in opposing pairs in the nose to control pitch and yaw, and in the outer wings for roll control. They were controlled by a separate stick. The trio of NF-104As was handed over to the Aerospace Research Pilot School at Edwards Air Force Base, which was commanded by Colonel Chuck Yeager. In November 1963, Major Robert Smith set an unofficial altitude record of nearly 119,000 feet. The next month, Yeager attempted to beat this, but encountered a severe, unrecoverable pitch-up at 104,000 feet. The aircraft fell into a flat spin. Yeager ejected, but was seriously injured. Despite the addition of a stick pusher system, the high alpha pitch-up and subsequent flat spin remained one of the Starfighter's principal vices for pilots who pushed the aircraft just a bit too hard. It had a good rate of roll, but was not particularly maneuverable, requiring good energy management to extract the best from it in a fight. High-speed slashing attacks were the best tactic against more maneuverable opposition. It was very stable and fast at low level, which made it an excellent fighter bomber. Long, shallow landing approaches and no-flare landings were the order of the day, with careful attention paid to speed and altitude to stabilize the aircraft on the approach. Even with flat blowing, touchdown speeds topped 150 knots. The Starfighter was not a jet for the faint-hearted, and the accident rate remained high. For its initial role as an interceptor, the Starfighter was armed with an internal gun and Sidewinder missiles. As the aircraft's repertoire expanded to include air-to-surface duties, so did its weapons inventory. Initially, the aircraft had 5 stores carrying hardpoints. There were single pylons under each wing and another on the center line. The wingtips could mount either fuel tanks or sidewinders. The F-104G introduced the ability to mount 2 missile launch rails under the forward fuselage, allowing the carriage of both sidewinders and tip tanks. Located in the lower port side of the forward fuselage was a General Electric T-171E3 Vulcan cannon. The F-104 being one of the first aircraft to have this revolutionary 6-barreled rotary weapon. The weapon was later redesignated as the M61 and in improved form is still the standard US fighter gun. Up to 725 rounds could be carried in a drum behind the cockpit, which were fired at selectable rates of 3,000 or 6,000 per minute. The drum could be removed and replaced by an auxiliary fuel tank if required. The initial missile armament comprised the GAR-8 Sidewinder, which was redesignated as the AIM-9B in 1962. This was a heat-seeking weapon that could be fired in rear quadrant attacks. The AIM-9D and E was subsequently adopted. The most remarkable weapon carried was the Douglas MB-2 Genie, an air-to-air rocket with a nuclear warhead for use against bombers. Fired from a drop-down trapeze, it was test-fired but did not enter service on the Starfighter. Rockets were a favorite option for the ground attack role, and a number of types were used. This is the commonly seen LAU-51 19-round launcher for 2.75-inch rockets. They were often carried in pairs from the wing pylons. Free-fall bombs were also usually carried from the wing pylons. The 750-pound M117 general-purpose bomb was a common weapon in the Starfighter and the later Mark 80 series, such as the Mark 82 and Mark 83. Napalm tanks could be carried on the wing pylons and released at low level against personnel targets. A rudimentary precision attack capability was provided by the AGM-12 bullpup, which used radio command guidance. For the tactical nuclear bombing role, the F-104 initially carried the Mark 28, which required a labs over-the-shoulder delivery in its earlier variants. Later versions of the Mark 28 introduced a lay-down capability. The Mark 43 could also be laid down from a straight and level low-altitude pass and was a key weapon in the NATO inventory, issued to several air forces but remaining in US ownership. Nuclear bombs were carried singly on the center line. German aircraft operating in the anti-ship role could carry the AS-30 guided missile, and this, the MBB AS-34 Cormoran. This was a radar-guided anti-ship weapon. Two could be carried under the wings. Italy's F-104S upgrade introduced an additional stores pylon under the outer wings, raising the total to 9. It also had new weapons in the form of the AIM-9L all-aspect attack sidewinder and the AIM-7 Sparrow. The latter was superseded by an Italian development known as the Selenia Aspi. Early starfighters had quite basic radars as part of a rudimentary fire control system. The XF-104 had an APG-34 radar feeding the K-19 radar gun sight. It was replaced in the F-104A and C by the ASG-14T1 system. The F-104G had a much better radar in the form of the North American F-15A, known as the NASAR. This was a multi-mode radar that aided both air-to-air and air-to-ground operations, although not all operators had all the available modes. In the air-to-air role, it provided a radar search mode and target acquisition. While providing automatic tracking for a lead collision missile attack. An automatic lead pursuit profile for gun attacks, and a pursuit attack for missiles fired in the rear quadrant. In the ground attack role, it provided ranging information for visual bombing, ground mapping for all weather bombing and navigation, and had a terrain avoidance mode for low-level flight. Backing up the radar was a simple infrared unit mounted forward of the cockpit. This provided a modicum of night sighting capability by being able to spot air targets at some distance, and also supported the radar by providing angular tracking measurement. For navigation, the F-104G was one of the first aircraft to employ an inertial system, although it was unreliable and relatively inaccurate, and most missions were flown using dead reckoning and a map. Many starfighters were RF-104Gs, dedicated to the reconnaissance role with a variety of sensors. With the cannon removed, a number of camera and infrared sensors could be accommodated on pallets in the lower forward fuselage. Additional sensors could be carried in external pods, such as the Vicon pod used by the Canadians. Dutch and Italian starfighters used the Orpheus pod carried on the center line. This housed a forward-looking camera in the nose, a fan of downward and sideward-looking cameras behind, and an infrared line scan unit in the center. In keeping with the slim design and small size, the cockpit of the Starfighter was quite cramped, although by the standards of the day, the pilot had a good view outside. The early machines were fitted with a Lockheed-developed ejection seat that unusually fired downwards. This concept was adopted as it was felt that if fired upwards at Mach 2, the seat would not clear the vertical tail. Pulling the handle initiated a complex sequence that depressurized the cockpit, pulled the control column forwards out of the way, tightened the harness, applied leg restraints and ankle clamps, and blew off a ventral hatchway before the seat was ejected downwards. Apparently, it was safe to use above 500 feet, but US Air Force pilots were told to roll the aircraft before ejection at anything under 2,000 feet. Often this was not possible, and 21 pilots lost their lives attempting ejections with the seat. Clearly, this was unacceptable. Lockheed developed the C-2 upward-firing seat for the F-104C and F-104G, allowing escape at any altitude at airspeeds above 90 knots. Germany's aircraft initially had the C-2, but later had the Martin Baker Mark 7 seat installed, which had full 0-0 capability. Danish, Greek, Italian and Turkish starfighters also had Martin Baker seats. Compared to other aircraft of its era, the F-104 had a relatively simple cockpit. A gun sight above the instrument panel provided aiming and steering cues for the pilot. The original reticle-type sight of the F-104A and C being replaced in the G by a director sight. The entire top section of the instrument panel accommodated the primary flight and aircraft instruments. On the right-hand side were the engine instruments, including those for exhaust temperature, oil pressure, fuel flow rate, nozzle position, turbine gas temperature, and engine RPM. Next to the engine panel was an attitude indicator and instrument landing system. In the center of the upper panel was the horizontal situation display, which provided the pilot with bearing and distance information drawn from the aircraft's navigation system. Above it were the vertical speed indicator and angle of attack indicator. To the left of this was the Mach meter and barometric altimeter, outboard of which were a clock, G-meter, turn and slip indicator, and a UHF channel selector for the primary radio system. Below the main panel was the radar screen, surrounded by controls. To the right of the screen was a panel that included a radar antenna tilt control and a dial for setting ground clearance when the radar was used in the terrain avoidance mode. There were also dials for the cabin pressurization, fuel pressure, fuel quantity, and ground speed. To the left of the radar screen was a panel for controlling the infrared sight. Next to the main armament control panel, which included a counter showing how many cannon rounds remained. Below the radar screen, between the pilot's knees, was the special weapons control panel for arming nuclear weapons for those aircraft equipped to carry them. On the right side of the cockpit was a console with controls for a variety of systems, including the aircraft oxygen, TACAN navigation, lights, cabin environment, inertial navigation system, and position and homing indicator. The left-hand console had a radar control panel at the front, behind which was the autopilot control panel. There were also switches for the fuel system, UHF radio, and further aircraft systems. Powering the Starfighter was the General Electric J-79 turbojet. It was located in the central rear fuselage with a long afterburner section reaching to the variable exhaust nozzle. For access to the engine, the entire rear fuselage had to be removed, including the tail assembly. The J-79 was a landmark fighter engine, the first high-compression turbojet with variable stators. As well as powering the Starfighter, it was also used in the all-conquering Phantom. J-79s for F-104s were built in Canada, Europe and Japan, as well as by General Electric. Air for the J-79 was admitted through a sophisticated intake with a half-cone center body that compressed the air and formed a shock wave in the inlet. The F-104 aircraft had an even more advanced intake with a double shock cone that allowed even greater airspeed. Because the wings were so thin, all the Starfighter's internal fuel had to be carried in the fuselage. The only available space was behind the cockpit and avionics equipment racks and forward of the engine, including the space between the intakes. Internal fuel alone gave the Starfighter a very limited range, so wingtip tanks of 340 US gallon capacity were usually fitted. The tanks not only provided much-needed extra fuel, but also helped damp wing oscillation and reduce the induced drag caused by air spilling around the wingtips. Large tanks could also be carried under the wing pylons, a regular fit for missions such as tactical nuclear strike, in which only one store was carried. The F-104 could also mount a bolt-on refueling probe on the port side of the forward fuselage to allow in-flight refueling. It was used mainly by US Air Force starfighters and principally for ferry flights. The nose wheel retracted forwards in single-seat aircraft and backwards in two-seaters. The main wheels had to be crammed into the packed fuselage and were mounted on widely splayed oleo struts to provide sufficient track for stability. The wheels twisted through 90 degrees as they retracted so that they lay flat in the lower belly. Control surfaces were relatively simple, comprising a single-piece rudder for yaw control, outboard aileron sections for roll, and a single-piece all-moving stabilator at the top of the fin for pitch control. Thanks to its tiny wing, a clean Starfighter had an impossibly high landing speed, so high-lift devices were employed to get the landing speed down to an acceptable limit. The entire leading edge formed a drooping flap. While the inboard sections of the trailing edge mounted large flaps. The flaps were later also employed to improve combat turning performance. By themselves, the flaps were not enough to get the landing speed down, so a boundary layer control system was installed on the trailing edge surfaces, the F-104 being the first operational warplane to have this feature. BLC, better known as flap blowing, employed compressor bleed air being ducted to 55 nozzles along the upper surface of each flap. This minimized boundary layer turbulence, so entraining more air across them and increasing their efficiency. Landing speed was reduced by around 17 knots as a result. Landing speed was still high, so stopping the Starfighter was a major issue. As well as its wheel brakes, it had large air brakes that deployed from the sides of the rear fuselage. There was also a landing chute packed into a compartment that dropped down from the lower rear fuselage. If all else failed, the F-104 had an airfield emergency arrestor hook under the rear fuselage, forward of the brake chute. Initial Starfighter deliveries began to the Air Defense Command in January 1958. A few YF-104As were delivered, along with production aircraft to speed service entry. In late 1958, some ADC F-104As were deployed to Formosa as a deterrent to Communist China. In 1960, the F-104As were handed over to the Air National Guard, the squadrons being dispatched to Europe during the 1961 Berlin Wall crisis. The Guard also later received F-104Cs. The C models had initially been delivered to Tactical Air Command for fighter-bomber duties, being placed on alert during the Cuban Missile Crisis. They also served in Vietnam, losing one aircraft to a MiG fighter in the process. They were too short-ranged for effective use in either the fighter escort or fighter-bomber roles. F-104As and Bs were supplied to Nationalist China in 1960, and they were followed later by large numbers of F-104Gs, which remained in service until 1998. Pakistan also received F-104As and Bs and used them to good effect in the 1965 war with India. Between 1958 and 1961, 5 important NATO nations chose the F-104G to equip their fighter, recce and tactical strike fleets. To cater for the enormous demand, 5 new production lines were established in Germany, the Netherlands, Belgium, Italy and Canada. The Canadians used their CF-104 Starfighters primarily as nuclear bombers based in Europe, while Germany's mix of interceptors, fighter bombers and reconnaissance aircraft were distributed between Luftwaffe and German Navy units. There was also a large training detachment in the United States. In Belgium, the Starfighter equipped 2 interceptor squadrons, 2 strike units and a conversion flight. The Netherlands also had fighter and fighter-bomber units, as well as a specialist reconnaissance squadron. Similar roles were performed by Italy's Starfighters. Other NATO nations also joined the Starfighter Club, including Denmark with 2 squadrons, Norway with another 2, and Spain with a single unit. Either side of the Aegean, both Greece and Turkey became major Starfighter operators, acquiring new-build aircraft and large numbers of F-104Gs passed on from other air arms. In the Middle East, Jordan received 2 squadrons worth of ex-US Air Force F-104As and Bs for air defense duties. At around the same time that NATO was adopting the Starfighter, so did Japan, and yet another production line was established to build the single-seat F-104J and 2-seat F-104DJ. Japan's aircraft served with 7 squadrons and were optimized for air defense. The Starfighter enjoyed a long military career, Italy being the last country to operate the type, having updated the fleet at least twice to maintain its viability. The last bowed out in December 2004. Away from the military, NASA operated a large number of Starfighters on a wide variety of test duties. The fleet included 3 F-104Ms used for astronaut training. A handful of F-104s also found their way into civilian hands in America, operated mainly under contract to the military to provide test support and chase aircraft for various trials programs. The initial mission entrusted to the Starfighter was air defense. It could use its blistering speed and climb performance to reach incoming hostile aircraft in a much shorter time than was possible with earlier types. In the air defense mission, Starfighters were held on alert at key places, particularly in defense of major cities. The armament consisted of just the gun, and 2 AIM-9B sidewinders. When an alarm was sounded, the starfighters got airborne as quickly as possible. They climbed swiftly and accelerated to supersonic speeds to meet the threat. Direction commands were received over the radio. As the starfighters neared their targets, the ASG-14 radar was used to find the targets at shorter range, allowing the pilots to set up for the attack. As the early versions of the Sidewinder were strictly tail chase weapons, the pilot had to position his starfighter behind the target. In later interceptors, this could be performed automatically, but in the F-104, the pilot had to work out the intercept solution himself. Depending on the target's relative speed and altitude, the starfighter pilot aimed to curve in from slightly below or level or from above, this profile providing a greater overtake speed. With the starfighter positioned in the target's rear quadrant, the AIM-9s were fired. At this point, the pilot could turn away from the attack, but usually followed the sidewinders to ensure that they hit. If they failed, or if they did not cause much damage, then the pilot would have to make a gun attack. Maintaining a healthy overtake speed allowed the pilot to close within its gun's range rapidly, but it also placed the F-104 within the range of the deadly tail guns of Soviet bombers, so it was not a practice to be taken lightly. Together with its speed performance, the F-104 could also reach considerable altitude, and partial pressure suits were worn for some missions. The F-104 certainly had the performance for the air defense mission, but it suffered from short legs, especially when it was carrying sidewinders. As such, it made an excellent point defense interceptor, but was not ideal for defending the United States. Accordingly, the type increasingly flew air-to-ground missions, especially after the F-104C was introduced. Its systems were not sophisticated enough for accurate high and medium-level bombing, so its ordnance was delivered from low level or in a dive. The dive attack was the most accurate, but it did expose the aircraft to more ground fire than a low-level attack. Ultra-low-level attacks were the most survivable, but accuracy was not as good, and care had to be taken to avoid damage being caused to the aircraft by the effects of its own weapons. In the attack role, the F-104 could strafe targets with its cannon or fire salvos of rockets from wing-mounted pods. It could drop a range of conventional free-fall bombs. And napalm, which was particularly devastating against troop concentrations and soft-skinned vehicles. The F-104C also introduced another capability that was to dominate the aircraft's role in Central Europe, the delivery of tactical nuclear weapons. In the tactical nuclear role, the F-104 was tasked against key targets such as airfields, armed with a nuclear bomb on the center line, like this Mark 28, or here, a Mark 43. Fuel tanks were usually carried. With this loadout, the F-104 raced towards its target at low level, relying on its excellent low-level speed to survive. Early tactical nuclear weapons could not be dropped from a straight and level low-altitude pass like a conventional weapon. Instead, the bomb had to achieve a certain altitude so that fusing mechanisms could complete their circuits and so that the launch aircraft could escape the area. However, a high-altitude launch was at odds with the low-level ingress. To overcome this, the low-altitude bombing system, or LABS, was introduced. Also known as the over-the-shoulder delivery, or the idiot's loop, LABS used a simple timing mechanism to release the bomb in an upward climb. The F-104 flew directly across the target at low level. As the target was crossed, the pilot pulled the aircraft into a constant G-climbing maneuver. the lab system began measuring the elapsed time. Just after the aircraft passed the vertical, the bomb was automatically released. The bomb continued to climb ballistically until it finally ran out of energy, toppled over, and fell back to Earth. If labs had done its job and the pilot flown the maneuver accurately, it landed right on the target. All this took some time, allowing the aircraft to continue the loop and then half-roll as it dived back down to low level. By the time the bomb hit, the aircraft had left the immediate vicinity and was running away at supersonic speed in a different direction from its ingress. When the bomb detonated, the F-104 was theoretically far enough away to survive the pulse of the detonation and flying fast enough to outrun the blast effect. In the 10 years following the end of World War II, aircraft performance leapt forward at a pace unmatched in any other era, driven on by jet engine developments and advanced aerodynamics. North American's F-86 Sabre fighter edged right up to the sound barrier, while the follow-on F-100 Super Sabre punched right through it. However, the F-100 was only marginally supersonic, and even as it was entering service, new and more ambitious fighters were on the drawing board, spurred by experience of pilots in the Korean War who demanded more speed, more altitude, and better climb performance. Convair focused on delta wing technology, building on captured wartime German research. Its F-102 Delta Dagger eventually delivered Mach 1 plus performance, but only after a major redesign. Lockheed, on the other hand, had its sights set on a much higher prize, Mach 2. To get there, the company would have to develop a whole new set of aerodynamics, discarding the swept wing along the way. Lockheed had emerged as a major fighter builder during the war, its P-38 Lightning setting the standard for long-range twin-engined fighters. It became the Army Air Force's main fighter in the Pacific War. By the end of the conflict, Lockheed was delivering the United States' first operational jet fighter, the P-80 Shooting Star, which bore the brunt of early jet operations in Korea. The P-80 also provided a firm foundation for more capable straight-wing designs, such as the radar-equipped F-94 and the T-33 trainer seen here. Led by charismatic designer Clarence Kelly Johnson, Lockheed also dabbled with swept-wing technology, producing the XF-90 that first flew in June 1949. Although firmly based on the P-80, some elements of the Starfighter design, notably the tip tanks, can be seen. The XF-90 was underpowered with its original J-34 engines and needed rocket assistance to get airborne. Performance was also disappointing in the air. There was no way that more powerful engines could be accommodated in its airframe, so it was passed over. However, experience with the XF-90 may have been a factor in Johnson choosing a straight wing for the Mach 2 design, and may also have influenced the decision to scale down rather than up. In March 1952, Johnson and his team set to work on a lightweight, high-performance fighter. An extremely thin wing held the key to the project. As well as tunnel tests, many wing designs were tested using scale models mounted on 5-inch rockets. Many showed unacceptable flutter, like this hollow wing, and this swept wing design. In some cases, the flutter resulted in catastrophic failures. However, using these tests, Lockheed arrived at a final, stable design. which was also tested with scale models of wingtip fuel tanks. The tail design was also tested using the rockets. The final result was known as the Lockheed L-246 or Model 83, of which two prototypes were ordered by the US Air Force as the XF-104. When it emerged, the F-104 was a remarkable futuristic aircraft. Johnson and his team had wrapped the smallest possible fuselage around the most powerful engine of the day, the General Electric J79. To keep the wing completely clean, everything, pilot, undercarriage, systems and fuel had to be crammed into the pencil-slim fuselage. The wings were tiny and of a highly advanced symmetrical section. The thickness-to-chord ratio was an unprecedented 3.36%, and the leading edge had a radius of just 0.41 millimeters, sharp enough to cause serious injury to clumsy ground crew. The wings were angled down to destabilize the aircraft in the rolling plane and also to offset the enormous induced drag of such a short-span wing. The one-piece, all-moving tailplane was mounted high on the fin to keep it out of the dirty air streaming back from the wing. However, the T-tail arrangement could mean problems at high angles of attack when the wing could blank the tailplane, leading to a loss of control. Lockheed installed a stick pusher system that attempted to overcome this. The J79 engine wasn't ready for the two XF-104 prototypes, so they both flew with Curtiss-Wright J65 engines with simple hemispherical air intakes and a prominent pen-nib fairing above the exhaust nozzle. Tony LeVere took the XF-104 aloft for the first time on the 28th of February 1954, during a short straight hop from the Edwards Air Force Base Dry Lake runway. On the 4th of March, LeVere undertook the first full flight. He was joined by Herman "Fish" Salmon in shouldering the brunt of the early test flights. Even with its J65 engine, the XF-104 immediately displayed blistering performance, achieving Mach 1.79 in March 1955. But there were also many problems, hardly surprising for such a radical design. In April 1957, Fish Salmon had to eject during early gun-firing trials with the loss of the second prototype. LeVere also had his moments. He had to make a brave dead-stick landing in an aircraft whose power-off gliding characteristics were more like those of a brick than a flying machine. In February 1956, the first of 17 YF-104A pre-production aircraft joined the trials fleet. They differed in several key areas, most notably by being powered by the intended J79 engine. They also had the production intakes with a half-cone fairing. This feature was considered so secret that early photos showed aircraft with a metal cover hiding the intakes. YF-104s also introduced forward retracting nose wheels, and the last aircraft was built with a ventral fin, curing a tendency for the aircraft to snake in flight. Production F-104As differed little from the YFs, and the first flew in February 1956. Aircraft built without the ventral fin soon had it fitted. The F-104C that followed had an uprated engine and incorporated a centerline pylon for the carriage of a single nuclear bomb or drop tank. Maximum takeoff weight was increased. Complementing both F-104A and C were the F-104B and D two-seat trainer versions. The trainers retained some combat capability, including the radar and Sidewinder missiles, but lost the internal cannon. All but the first 6 F-104Bs were built with a fully powered extended chord rudder to improve directional stability and control authority. The F-104F was a similar interim trainer built for Germany. The extended rudder was the most obvious external feature of the F-104G model developed for NATO air forces, although it was also very different under the skin. A completely new avionics system was accompanied by a structural redesign to equip the G for life as a low-level, high-speed fighter bomber. The last major production version was the F-104S, built in Italy. The Sierra had a further uprated engine and the ability to fire the Sparrow radar-guided missile. Accommodating the avionics for the latter meant that the gun had to be deleted. It had 2 extra pylons under the wings. A number were upgraded to ASA standard, with the gun reinstated an as-speed missile capability. Over its long career, the Starfighter was used for a number of trials programs, including the remarkable zero-length launcher project, which tested the use of rockets to blast F-104s into the air. The Germans also converted one to an unstable control-configured vehicle to investigate fly-by-wire control systems. It flew for a while with a second tailplane mounted on the spine to destabilize it. There were also a number of follow-on proposals, including the CL-1200 Lancer. This had a low-mounted tailplane, high-mounted wings, and a TF-30 engine, but did not progress beyond mock-up stage.
ステルス爆撃機 B2 スピリット。冷戦の終結で生産機数は大幅に減らされましたが、世界最高の爆撃機であることに疑いの余地はありません。次号ではその B2 を徹底的に解剖します。次号もぜひお買い求めください。